Today we are going to be teaching you about the Munkres assignment algorithm, also known as the Hungarian one. The Munkres algorithm was made to tackle the problem which is named the assignment problem. This is where you have a set of agents and a set of tasks, where any of the agents may perform any of the tasks, but only one of them. This means the job of the algorithm is to find the best way to match the agents to a task, and the Munkres algorithm does this by minimizing costs for each agent taking on a task. Some assumptions to the algorithm are that the amount of agents is equal to the amount of tasks, and that the algorithm is always trying to find the minimum cost. First step to the algorithm is to create a matrix of n by n size. This is where each element will correspond to the agent taking on its task, but this is the cost.
For each row in the matrix, we want to find the smallest element and subtract this from every element in the row. So for example, in the first row, we've got 5, 6 and 4, where 4 is the smallest. We subtract this from every element, so instead of 5, we'll have 1, instead of 6, we'll have 2, instead of 4, we'll have a 0.
The third step to the algorithm is exactly the same as the last, but you do it for each column and only if every column doesn't have a 0. So the minimum of this column is 0, so we don't need to worry. But the minimum of this column is 1, so we need to subtract 1 from each element. Here we have zeros in this column as well. So this step also ensures not only the rows have zeros, but also all the columns.
For step 4, we have to cover the 0 elements with a minimum number of lines that it's possible to cover them with. So as you can see in this matrix, we could cover them with 3 lines, going this way, this way, this way. However, this is not the minimum. If we go down this column and across this row, we've used 2 lines and we're covering all the 0 elements. If the number of lines equals the number of rows, however not in this case, then you go straight to step 7. However, we'll have to go to step 5 as we've got 2 number of lines and 3 rows.
In this step, we need to add the minimum uncovered element to every element that is covered by 2 of these horizontal and vertical lines, and then minus this value from each uncovered element. So in this case, the minimum uncovered element is 1. So, and the only element that is covered by 2 lines is 3. So here we need to add 1 to the 3, 4, and then subtract this value from every uncovered element. Making this 0, 0, 0, and 6.
For step 6, we have to cover the 0 elements with a minimum number of lines again. If the number of lines do not equal the number of rows, then we have to go back to step 5 to be able to reduce the matrix even more. In our example, we can cover the matrix with 3 lines. This means that these 3 lines equal the number of rows, 3. However, we can also use a different scenario where instead of those 3 lines, we can go 3 lines down the columns, as this also covers all the zeros.
In this step, we need to select a matching in the matrix by choosing a set of valid zeros, that each column or row has only one selected. This row only has 1 0, so this means agent 3 is forced to take task 1. This means that whole task is wiped out. Now if you look at agent 2, he can only take on task 2. And this means that agent 1 can only take on task 3. As in our previous example, it's possible to have different variations that will lead to the same minimum cost, but we'll show you that in the example later.
In step 8, our final step, we'll apply the matching that we've just come up with to our original matrix. This should show you the minimum cost, which is the solution to the assignment problem. So here's our matching that we've just come up with. Agent 1 should take on task 3. Agent 1, task 3, can take the value of 3. Agent 2 should take on task 2. Agent 2, task 2, take the value of 2 and add that on. Agent 3 should take on task 1. Agent 3, task 1, get a value of 2, add that on. So the minimum cost should be 7. 3 plus 2 for 2. If you look roughly in the grid, that should be the minimum cost. Just please be aware that the examples that we use in 7 and 8 are different examples from 1 to 6. This is just for simplicity reasons. In our later example, we'll provide you with the harder explanations.
Now we're going to talk about our more complex example. Here we have a manager who has a 5-side football team. He wants to minimise the cost of the footballers, but footballers being footballers all demand different wages for what position they play. So here we're going to use the Munkres algorithm to find the minimal cost the manager has to pay.
Now following the steps we've just been through, we're going to subtract the minimum element from each row to all the elements. So now, from first row, minimum element is 7. We want to subtract that from every single element in this row. 60 minus 7, 53. 10 minus 7, 3. 15 minus 7, 8. And 50 minus 7, 43. 7 minus 7, 0. Now, onto the next row, we want to subtract the minimum element again. So minimum element is going to be 25. Minimum element of the third row is going to be 5. Minimum element of the fourth row is going to be 2. And minimum element of the fifth row is going to be 10.
We've now put the new values into the matrix. We can move on to the next step, which is doing the exact same but with columns. This one, the minimum element in the column is 0, so nothing needs to change. Here the minimum element is 3, so we need to take out 3 of each of these. This makes this one be 0, this one be 4, this one be 42, this one 10, and this one 27.
Now with the new values in the matrix, we now have at least a 0 in a column and row. Now we need to draw lines over the uncovered zeros. So we want to find the minimum number of lines. We could do 5 lines, going down there, there, or vice versa across the rows. However, this is not the minimum number of lines. The minimum number of lines that we found, going down the column, run across this row, down the column again, down the column again. This is 4, which is less than 5.
The next step of the algorithm is to fill in the uncovered elements. First of all, we need to find the minimum uncovered, which is this 2 here. This means we have to add this to every point on the matrix where it's covered by 2 lines. So that'll be here to change it to 55, sorry. Here to 45, and here to 2. Now we need to minus 2 from all the uncovered elements. So this one's 2, 40.
Now we have to cover all the zeros for the minimum number of lines again. So once again, you could do 5s, that way, etc. However, that's not the minimum number of lines. Minimum number of lines, one going this way, one going this way, one going this way, one going this way. That makes 4 again. So likewise, as before, this doesn't equal the number of rows. 5 rows, 4 lines. So then we have to reduce the matrix again.
Once again, the minimum uncovered element is 2. This means on every element that has 2 intersections, we need to add 2. So this makes 55, 57, 15, 17, and 0, 2. Now we need to minus 2 from each of the uncovered elements.
Now with the new values in the matrix, we have to draw the minimum number of lines. This will be 5. We can either go across all the rows, or instead of that, down the columns. Either way, we'll have the same cost and the same assignment.
Now the number of lines that we have covering zeros is equal to the number of rows. We can now move on, as we know that there will be an assignment possible. As Steve only has 1 0 in this column, we know that he has to be a goalkeeper. Now the next one is Barry, who can only be a cam. After this, we have alternatives. So the first alternative would mean Paul could be a defender or a striker. So if we set Paul as a defender, that would then force Derek, who can't now be a defender, to be a centre mid. This leaves Bob, who can't be a centre mid anymore, so has to be a striker. The other alternative still has Barry as cam and also Steve in goalkeeper, as that's the only ones possible for them. But now this time, Paul could be a striker. That would mean Bob has to now be a central midfielder. And Derek would then be forced to be a defender. Now all of these are matched up together, and we have 2 alternatives of the same cost.
Now using the matching that we've just come up with, we filled in the matrix with the original value so we can find the minimum cost. So for alternative 1, Paul being defender, we got 10. Derek being a centre mid, CM, 35. Barry being a cam, got Barry cam 5. Bob being a striker, 4. And Steve, who's left as a goalkeeper, with 10. This gives a value of 64. So that'll be our minimum cost. Just to prove to you that the alternative 2 will also give minimum cost, we've got Paul as a striker. Paul striker 7. Derek as a defender, type defender 32. Barry as a cam, Barry cam 5. Bob as a centre mid, CM, Bob CM 10. And left with Steve as a goalkeeper again, Steve goalkeeper 10. Which also, if you add that up, that also gives 64. So this is the solution to the assignment problem.
To maximise the cost of assignments, find the largest elements in the grid, then subtract all the elements from this number. For example, in this grid, the maximum number is 30, so we subtract all the elements from this. We then apply the algorithm as normal. If we have a different number of agents to tasks, we can just create dummy agents or tasks so that the number of agents and tasks are equal. The costs associated with these dummies are the maximum value in the cost matrix. Once added, apply the algorithm as normal.
The overall time complexity for the Munkres algorithm is big O n to the power of 4. Most of the steps are big O n squared because we're looking at every element in the matrix. In a loop, we calculate the minimum number of lines. This takes big O n squared as we're looking at each element in the matrix. We'll keep trying to calculate the minimum number of lines at most big O n squared times, which means the final and overall complexity of the algorithm is big O n to the power of 4.